periodic elastic composites. So this work has been developed.
My presentation deal with possibility to give global description in the dynamic regime in elastic composite. And for this, I will investigate different cases that is represented by this graph. I will consider first weakly contrasted composite. That means composite where there is contrast but not very large contrast. I will first consider the case of large-scale dynamics. That means where the wavelength is significantly larger than the period. And then we'll go to another field that is the local dynamics. That is when the wavelength becomes smaller than the period. That will be the two first parts, and finally, so here you have large-scale dynamics, here you will have local-scale dynamics, and then we'll go to the case of highly contrasted composite, where you can get both large-scale and local-scale dynamics. So, to do that, we have to go from the local description to the global description. So the scale separation for this is a necessary requirement, and it is also sufficient. So this notion of scale separation is well known in case of, let's say, low frequency, but the question is, what is the meaning of scale separation at high frequency? So we'll speak about that. But now, assuming the scale separation, we will see how. We will use a classical two-scale asymptotic expansion, which is using the classical homogenization method, slightly modified, you will see, assuming periodic media, harmonic regime, small deformation, and linearity, means elasticity. So let's begin with the first situation for long wavelengths in weakly contrasted media. So this means this kind of situation. So in this case, the notion of scale separation is very well known. So you have long wavelengths in the media, and this means that the wavelength is much larger than the periodic size. So this introduces a small scale parameter. You have macrodynamics, and this implies that indeed physically, locally, you have a quasi-static local regime, and in consequence of the long wavelengths, the scale separation applies for the motion. This means that the motion inside the media will vary very slowly from one point to another one. So just few words about homogenization that have been already described previously. So you have in situation of elastodynamics. So the equation that governs the problems are given here with the classical stress, strain, elastic tensor, the balance of equation with frequency, density, and the effect of inertia. And this can be written in the similar form as this one, where you have the differential operator that is given here. Okay? So homogenization, you know that you have already seen that it introduces the two scale variables. This implies to make expansion of this differential operator, and in this different form. And what I would like to stress, it's because we have large fluctuation. This means that inertia terms will balance the macroscopic terms here. So just again, this is very classical. So the description is you make the expansion, you have a series of omega periodic problem to be solved. What I would like to stress is that in any case, what we get in this situation is that locally we have elastostatic problems with forcing terms that appears at different order. So when we solve that, we have at the leading order, we recover a classical macro elastodynamics with the effective tensor and the effective inertia that is given by the mean of the density. Okay, so this is the situation. We are fully in the situation where locally we are quite in a static regime, let's say quasi-static regime. So the interesting case is when you go, when you have no very large wavelengths, but smaller wavelengths, but still larger than the period, you have a weak dynamic that appears at a local scale. And to consider that you can introduce the corrector of the description, since in this case the scale ratio is small but not very small. So when, I will not give the details, but when it comes that you have an expansion of the motion with smaller and smaller motion that are driven by the systematically you recover the classical elastodynamic here, plus some homogenized diffracted source that come from the previous order. And this enriched elastodynamics demonstrate that you have to consider in this case a non-local elasticity, because as you see you have higher gradient that appears here. You have also to consider non-local mass, because as you can see the inertial effect have to be corrected not only by the displacement but the gradient and the gradient of displacement and so on. And this description is good enables to give the description for Rayleigh scattering in the composite. So you have this in this domain that we just present. So you have the classic elastodynamic, and when you go to the higher frequencies, that means to smaller wavelengths, you have the description of Rayleigh scattering that give you the unregistered elastodynamics. But what you can see here that this is something like a wall that with this approach we cannot cross, because we use the expansions. When we go here, the scale separation in terms of wavelengths becomes that doesn't apply. Okay, so what can we do in this domain? So that's what we consider now. We go to the situation when we have short wavelengths in this periodic elastic media. Always we consider that it is weakly constructed, so we are here. So we know that in this weakly contrasted composite and short wavelengths, we can have an exact description of block wave using block wave. But the point is that this block wave doesn't give you the possibility or not to have a macro description or not, and to see if there is some macro phenomena, how they can propagate. So this is interesting, but it doesn't give the response of a question of macro description. The second point that I want to stress is that in this case, obviously, since we have short wavelengths, there is no more scale separation for the motion. So the idea to get scale separation is the following. Can we obtain a macro description in this situation? So to do that, let's consider again what happened in the cell. So you have the problem that is given here, that is the classical elastodynamic problems settled on the cell. Now the inertia appears already at the cell level with here A is elastic tensor, rho the density. I just say that here in the presentation I will always consider that the density is constant, but in reality we can deal with non-constant density, and the result that I will present apply for non-constant density. Okay? So when we have this equation inside the cell, we this looks directly with rho constants as an eigenvalue problem. So you can define eigenmodes that are periodic eigenmodes. What does it mean? So 2 points. First point that is important is that here this is a typical periodic cell, but for the eigenmodes, I can show the eigenmodes in this typical cell are not necessarily the same, and there is more eigenmodes if you consider larger cells. So in this situation, contrary to usual homogenization, I have to say, okay, we have eigenmodes, but I have to define what kind of cell I consider. That is, I have to consider multi-cell, but to define this multi-cell. Okay. So what is the meaning of these periodic eigenmodes? That means that at this frequency, I will have in the media something like that. So if this is the period, I will have something that is reproduced exactly the same because it's periodic. So this means that the amplitude of the mode is the same. So the idea to get a scale separation is to say, okay, here what we will consider is that we can have a modal amplitude that vary at large scale. So instead of saying that the motion vary at a large scale, what we will say that the amplitude of the mode fluctuates at large scale. Okay? So this means that obviously if this vary at large scale, this is not the exact solution, and this means that we look what happens not at this exact frequency but around this frequency. And this idea has been suggested by and studied by Kraster in the paper of Kraster, Pishugin and Klapunov. So, in this situation that we will investigate, we will use a two-scale formalism that is very similar to homogenization, except two modifications. First, the frequency range. That means that we will investigate around the eigenfrequency of a given mode, and so we make expansion of the frequency. And the second one is that the cell is not necessarily the irreducible cell, but one multi-cell that we choose. Okay? So in the following, I will choose this frequency and the given multicell. And then the steps are very classical, expansions of the variable and of the and the differential operator. So with this assumption, what do we obtain at the leading order? So the problem that is given at the leading order in the local variable is this one. So using the two-scale expansion, so you will have a motion that takes this form, that is the local mode, and that is the amplitude that vary at large scale. This will be the case for simple mode, but at this frequency the model is double. You will have two amplitude, decomposition according to the two modes at the same frequency. If the mode is multiply n, you will have n amplitude that appears. So first I will consider the situation for simple modes. So the homogenization process is so the first order was this one, then we go to the cascade of resolution. So let's go to the second order. So what do we obtain? We obtain exactly the same problem as previously, except that we have source terms that come from the previous order. So these source terms has two components. But when we look at this problem, because it's periodic, we know that it is an eigen problem with the source terms, and the Freedom alternatives say that necessarily these source terms have to be orthogonal to the eigenmodes. So we have this condition to be respected. When we express this equality using the expression of the source terms, we can decompose it in two terms. It happens that this one, the mean, is equal to 0 because this specific terms is antisymmetric. So when the two terms are the same, this vanishes. And it only remains this one, but since this one is proportional to phi, the first corrector of frequency is equal to 0. So this means that at the leading order, this term disappears and you just have this one. And this means that the source is given here. It's proportional to the gradient of the amplitude of the modes. So we can solve this problem exactly using the modes as orthogonal basis. So we have the exact solution at the local scale. Then we go to the next order, and to the next order we have the same kind of problem with two source terms, one coming for the leading order displacement, one the first order displacement. Again, we have the freedom alternative, but since this displacement is known and this one is known also, this directly leads to the governing equation for the amplitude. So this means that this is the governing equation for the modulation of the mode, and this is not a motion. This is the amplitude of the mode that is driven by this equation. And what we obtain is that we have a governing equation that takes this form for the macro modulation. So this is around this eigenmode frequency. Two remarks. First, this tensor is based on the eigenmode, so it's an elasto-inertial tensor of second order, of the second round. It may be positive or negative, but it is symmetric. And this one, as you can see, this is something like a differential inertia that also may be positive or negative. So you can see that in this representation, according to A, if you consider A, you will have a very strong dispersion of the fluctuation of A according to the frequency. we can consider what happens for the double modes, and this will be more or less the same for multiple modes, but for double modes, as I told previously, the motion will be decomposed in two contributions according to the two modes. So when we go to the first order problem, we again apply the freedom alternative, but now we have two modes to apply. So there is two orthogonality conditions, and since we have two amplitude, this lead already as this order to a set of coupled equations that we resolved to a single equation here, and this single equation is of different nature than previously, since this elasto-inertial tensor is positive or zero, but not negative, and this one, as you can see, the differential inertia is always positive. So what can we say about these descriptions? If we can discuss more or less in the details, but I will just focus on the comparison between what we had previously and what we have now at short wavelengths. Several differences significant. First, at the low frequency we have a single description. Here we see that we have multiple modeling, since every modes give a specific equation for modulation. Okay. The second point is that previously we have three variables. That was the motion amplitude. Here we have as many variables as the mode is multiple, of the multiplicity of the mode. Here we have the classical stress and inertia concept that were enriched by high order terms. Here there is a fundamental change. It's very difficult to identify stress. I don't know what will be, and also about inertia. But as you can see, I put this all together. Why? Because what is very nice indeed is if we apply the high frequency modulation to the low frequency situation, it appears that we recover exactly this approach. Why? Because the motion amplitude, the translation, are the eigenmodes at the zero frequency. So this means that this high frequency modulation is already a description, involve already the description of low frequency description. So what we yes. So you will see this is very close to what I've presented Alexei Prof this morning. So here it's an illustration for a single spring and mass situation. Here we have the spring and mass clamped here and free here. There is 30 mass, so you can calculate 30 modes. What we get with the classical homogenization is this situation here, when the motion from one point to another one is very close. But what we get with modulation is this kind of situation. For example, if I consider two cells, so in two cells I have a single mode that is opposite motion. That was exactly what I've presented by Alexei Prof. And you can see that what we compute is not the exact motion, but the amplitude here, or the amplitude here around this eigenfrequency. But we can consider the situation of three cells with double modes, and you can see with three cells we recover this fluctuation here, even if the motion are completely very fastly moving. Okay? This is 1D, but we can do it in 3D, but I think I would like to speak about more things, so I squeeze that. And now, okay, c'est bon. And now let's go to the other situation. What we have seen, we have two situations very, let's say, very different indeed. Either you have almost quasi-static regime or almost full dynamic regime. Can we obtain situation where both together? That will be interesting. And the answer is yes. And it's need to consider highly contrasted materials. So on this point, this looks very much to metamaterials with inner resonance. I would like to stress for the people that are working on these topics, the paper, all paper of Oriot and Boutin, that presents more or less all the physics, and that is nobody knows, because at this time it was not the fashion for metamaterials. But in this, if you read this paper, you will see that most of the results were already identified. So I suggest for the people to look at the literature in this point, much before that Milton and Willis and anyway, That's what I call the codynamic regime. How can we get the large, long and short wavelengths at the same frequency? I will consider a contrasted B composite. For the one constituent I call C, because it will be the carrying constituent for the wavelengths. This should be such that at this frequency the wavelength is much larger than this size, so we have the scale separation as usual, and we'll be in quasi-static local regime. But we have also the second one, that is the air constituent, like resonating, because at the same frequency I would like to have the wavelengths of the size of the ear. So we'll be in dynamic local regime. If we consider that the density of the two materials is the same, this condition here implies that if we consider the stiffness contrast, it is defined by the scale ratio that is given by the ratio between the two wavelengths related to the square roots of the modulus. So this means that to have this situation, you need to have elastic modulus of the resonating materials that is 2 orders smaller than for the carrying materials. So I will go fast for the homogenization because it's quite standard. You just have to rescale the elastic coefficient of the resonating soft resonating materials. Since it is very soft at the 2 first order, everything is like if these materials was not here. So we don't care. But at the next order, at the second order, when you solve it, now appears at the boundary. When you make the balance of the force in this domain, at this boundary appears the stress that appears inside this domain. And in this domain, that is the resonating domain, you have a dynamic problem to be solved. And this is simply that, like water in the glass, you know, you move uniformly the glass and the water is moving inside in resonance. So you have an effect of resonance. You can describe this internal response. So the motion inside the resonating system is fluctuating, and this means that these terms that is due to the resonance can be either positive or negative. So you have the classical effect of classical effect of negative stiffness that introduce apparent math, that is tensor effects, frequency dependence. You have band gaps at long wavelengths. Okay, so this is not short wavelengths but long wavelength situation. So we see that with these contrasted materials we can build negative mass system apparently. The question, but you see that elasticity is very, very classical. You have the usual elasticity. Now the question is, can we obtain a inverse situation where you have negative elasticity? And this is slightly different. And to obtain negative elasticity, what you need is that the elasticity is inside the source term. So this is the case in porous media. When you have porous media, you have the flow in the porous media, and we have to balance the flow, the mass balance, and here appears the elastic stiffness. So if we put inside this porous media Helmholtz resonator, we obtain just a modification as previously for the mass, but now it's a modification of elastic stiffness that maybe you can see directly here either positive or negative. And to conclude, I would just like to say that that's perfect. Just want to say that for this kind of material, for some example of application, this is a porous material where the grains are already done by resonators. So you see it is that a ping pong ball with some tube for drinking lemonade or vodka, and you have here these holes that make that is a resonator. So if you make exactly this kind of material and you look at the absorption coefficient, so according to the the frequency. In black, you have the curve where the balls are without resonator, so not modified balls. And here you have in the different situation. I will explain if you want, but correspond to situation where the balls are completely resonating, designed to resonate at given frequency. So you see that there is some application in terms of absorbing coefficient. So finally. No, just to say for Francesco that I think that Francesco will be happy because we lost for this higher modulation. We lost the concept, Cauchy concept, but we don't have a Piola description. Anyway. But anyway, what is important is that its high frequency, elasticity and inertia are coupled. You cannot separate as usual. And in my opinion, it's interesting, at least theoretically, I don't know practically, to have the wider parameter that you see that the motion can be replaced by mode amplitude. And I stop here. Thank you very much.